All right, so hello everyone. I'm Norman Weilberger, and today we're sort of finishing up this course on differential geometry, this beginner's course in differential geometry, at least for the time being. So we're going to talk about today about Gauss and his view of curvature, and say a little bit more about this theorem Gregium, and connect also to some discrete differential geometry. So the story that we sort of were developing last time might be summarized with a picture, something like this. That we have a surface, here's S, and here's a point on SP. And at that point we have, of course, the tangent plane, which we denote by T sub P of S. And that tangent plane has a normal vector. In fact, it has a unit normal vector. So n of p is the unit normal. And we're going to use that to define the Gauss-Rodriguez map. N. That maps to the unit sphere, S2. Okay, so we're going to take this point P and we're going to send it to the normal direction, which we'll write like this. So here's that same n of P. And the tangent plane here is really the same direction. So this is really, again, the tangent plane to S or to S2 at n of P. And this is the Gauss-Rodriguez map. And we're particularly interested in, say, the derivative of this map, which takes tangent vectors here to tangent vectors here. And so the derivative, say denoted by dn of p, will be a linear map. Okay, now Gauss's point of view was that surfaces are described parametrically. So in addition to this picture, we also have this parametric picture where, let's say, down here is the parameter space that Gauss uses to set up the surface in the first place. So here's the UV plane, let's say. It's our parameter space, and perhaps some rectangle in the UV plane. And we have some coordinate chart R, which is actually a vector value function, that takes this rectangle onto a piece of the surface, well, including our point P. And of course, then we could compose this. We could go first with R and then with N. So we could also think of this map here, which would be R composed with N. Okay, so in terms of these things, Gauss's understanding is that the curvature of the surface S at P is basically the determinant of this derivative map, dn of p. So it's in a ratio of areas. So let's say the d area of S2 over d area of S. It's a local comparison between a small area here and the corresponding area over here. Now, because Gauss thinks of everything in terms of these charts, you could also naturally ask, well, suppose that everything comes from some point, say, Q over here. So suppose Q gets mapped to P. Then it's sort of reasonable to ask, well, what's the determinant of the map R at Q? So the determinant of the map R, or well, maybe dr. Well, that's going to be the determinant of a certain 2x2 matrix that we talked about, EFFG, which is EG minus F squared. And This determinant over here, the determinant of the derivative of n composed with r, is also a determinant of another 2 by 2 matrix, often denoted little e, f, f, and g. So that becomes e, f, or e, g minus f squared. I'll explain what these things are in a second. But in terms of then of these two determinants, we can understand the curvature as the determinant from here to here as the ratio of determinants, one from here to here and one from here to here. So we can write this as the determinant, well, it's just going to be e g minus f squared over capital E g minus f squared. Basically, the fact that when you compose linear transformations, the determinants multiply. So this determinant times this determinant is going to be this determinant. And so that means that this determinant is going to be the ratio of this determinant divided by this determinant. Okay, so what are these numbers actually? Okay, so the numbers are, well, first of all, E was, they're all in terms of the derivatives of this R map. So E was R sub U dot R sub U. So we're taking the partial derivative of this R in the U direction. And we're getting two vectors, R sub U and R sub V over in this tangent plane. And then we're taking the dot product of RU with RU, that's E, and then F is RU dot RV, just the same as RV dot RU, and G equals RV dot RV. And these numbers make up what's called the first fundamental form. So over here we have the first fundamental form, which is really a quadratic form on this tangent plane. And then over here, the little e's, f's, and g's are given by, so little e is this dn sub p r sub u. So if we take what the image of R sub u is under this derivative map, and then take the dot product with RU itself, then we get the quantity E. And because the normal is perpendicular to R sub u, we can rewrite this as n dot n, which is the normal, dot R, the second derivative of u with respect to, of R with respect to u. Similarly, we have F equals dn sub p of R sub u dot R sub v, which is dn sub p R sub v dot R sub u. And that's n dot R sub v, or R sub, say, u v. And little g is dn sub p of R sub v dot R sub v, which is also n dot R sub v v. Okay, these are formulas found in almost all classical texts. And in fact, this is the standard approach to curvature in most classical texts. So the way we've approached it is a little bit untraditional. Most classical texts follow Gauss in basing everything on a parameterization. All right, so we haven't done that because we've been more interested in surfaces as sort of algebraic surfaces. But nevertheless, this is an important alternative way of thinking, and these formulas are important formulas to have seen. And they're, in some sense, relatively uncomplicated. You have to have a parameterization. You're going to have to compute an n, which is a normal. Okay? And I'll remind you that the normal was obtained by R sub u cross R sub v divided by the length of RU cross R sub v. There's a bit of a square root floating around there with that n. Okay, so a natural question is, all right, this is a nice view of curvature, but why is it really the same as the curvature that we are thinking of in terms of sectional curvatures that we've studied earlier? So to make that clear, let's have a look at a computation that sort of shows the equivalence of the two ways of thinking. So I want to do the simplest possible computation. So we're going to justify this view, let's compute this derivative of this normal map at a point P for a paraboloid, a normal paraboloid of the form that we like, 2z equals ax squared plus 2bxy plus cy squared at the point P equals 0, 0, 0. So we're going to take our favorite sort of object, a normal paraboloid with axis perpendicular to the xy plane. We're going to look at everything at the point P, which is the origin. I want to see what this normal map does. Okay, so let's to do that, we have to understand what the normal looks like at nearby points to P. So let's take a nearby point, say RS. So here's a point RS in the plane. And we're going to go up to a point on the surface. Say this will be the point RS and say U. We might introduce Z is equal to f of xy, which is, okay, 1/2 of ax squared plus 2bxy plus cy squared. So U here is just f of R and S. So a natural first question is, what is the normal at that point there? Well, this is pretty easy because the paraboloid is a normal or level surface for f of xy minus z equals 0. And so therefore the normal is given by the gradient of this. So n will be df dx, df dy, and minus 1. And because this is nice quadratic, it's easy to calculate what this is. So the partial with respect to x will be a times x plus b times y. And then partial with respect to y will be b times x plus c times y. And there will be a minus 1. So then unit normal, so at the point RSU, the unit normal n would be, well, we'll just plug R and S into here, AR plus BS, BR plus CS, and minus 1. And then we have to divide by the length of this thing, so an AR plus BS squared plus a BR plus CS squared plus a 1 all to the half. Okay, so now what we're interested in is, suppose that we're going in this direction. Suppose we head in this direction. and look at the corresponding curve up here, and look at this normal here, and this normal is going to change. And let's differentiate this dependence on in the direction t. So if we take d by dt of, okay, this is the normal at rs, the normal at, say, t times r, t times s, and u of t r ts at t equals 0, that's going to be the derivative of these normals at the point 0. All right, so explicitly that would be the derivative. Let's put a t in everywhere here. So up here there'd be a t times ar plus bs, t times br plus cs, well, this thing is always minus 1. And then divided by, okay, there'll be t squared times ar plus bs squared plus a t squared, okay, plus br plus cs squared. I'll put that all in brackets. Plus 1 all to the half. Okay, I want to differentiate that and then set t equal to 0. All right, let's see if I can do that here in this little corner. So it's the quotient rule, so I have to take the derivative of the top. The derivative of the top is just this vector ar plus bs, br plus cs, 0, times the bottom. And then we're going to evaluate the bottom at t equals 0. So the bottom evaluated at t equals 0 is just going to be 1, because the t equals 0 means that the whole thing will be 1. And then minus the top times the derivative of the bottom. Okay, so the top, whatever it is, times the derivative of the bottom. When we differentiate the bottom, there'll be a 1/2, and then there'll be something to the minus a half, and then we have to by the chain rule, take out the derivative of what's inside, and that will give us a 2t. Okay, and that's all we care about is that 2t there, because when we set t equals 0, that's going to be all 0. Okay, so that's all the numerator. And then we have to take the denominator squared and set t equal to 0. So when we do that, we also get 1. So this is all set at t equals 0. So that will die, and then we'll have finally just ar plus bs comma br plus cs comma 0. Okay, so let me write that down somewhere. Maybe I'll write it here. Okay, so this dn map at 0, 0 takes rs, takes that vector, and sends it to, so that's the direction that we're sort of looking in. We're looking in the direction rs, we're evaluating normals and taking the derivative as we go in that direction. And we get that direction there, and I can write that as rs times the matrix A, B, B, C. That's what we've got. AR plus BS, comma, BR plus CS. So what we have demonstrated is that this shape operator, the derivative of this normal map, really ends up being just this quadratic form that we've called the Hessian all along. All right, this is just what we've been calling the Hessian. This is the quadratic form, and that's how we define the curvature, or how we computed the curvature for this thing at 0 in the first place. So the curvature, Gauss's view is that the curvature is the determinant of A, B, B, C in this case, which is AC minus B squared. And this agrees with our earlier derivation. With our earlier work. So basically, we've convinced ourselves that Gauss's insight is correct for a normal paraboloid. And since it's correct for a normal paraboloid, by our usual approximation argument, it's going to be valid for a general surface. Because a general surface, up to the terms that we're considering, is basically a normal paraboloid. All right, so this view of curvature is really not any surprise, because this exactly fits with one of our views of the curvature of a curve. So I remind you that if we had a planar curve, one way of viewing the curvature was as the curvature was 1 over the osculating circle. And another way of viewing that is if we sort of think of the tangent vector moving along, that k times ds was equal to d theta. Well, k equals d theta over ds, where theta is an angle formed by, well, the normal vector or the tangent vector. Depends which one you're interested in, but it's both equivalent because they're 90 degrees to each other. So remember that in such a situation we had some formula like this, that if we integrated the curvature, I guess it was small, if we integrated the curvature ds, then we got the change in angle. If we're integrating around some section of the curve, or along some finite curve. So the same kind of reasoning now applies to our two-dimensional situation. So now we have a situation that if we have a surface S, and we have some portion of the surface, let's say there's S and there's some portion U, and we have our curvature function. So at every point we have K of S, the Gaussian or second curvature. If we think about the normal over here on the S2, the image of this will be some part of the two-sphere. And Gauss is telling us that the relationship between a small area here and a small area here is just that we are multiplying by the curvature. So it's exactly the same kind of story as we had here, and allows us to conclude that if we integrate over U, the curvature of S, well, with respect to area, so let me write d area of S, then we're going to get the area over here of the image of the normal Gauss-Rodriguez map. We get area of the image of n. Because infinitesimally, k times d area here is d area here. In particular, if the surface S is like a sphere, if S is homeomorphic, is say a convex surface, homeomorphic to a sphere, then the integral over S of K of S d area, maybe I'll write dA of S, will just be the total area of the sphere, area of the unit sphere, which is 4 pi. And that's a two-dimensional analog of the fact that if you have a curve like this and you integrate its curvature ds along the curve, you get the area of the circle of radius 1, which was 2 pi. All right, this reasoning has a nice sort of application to polyhedra. Okay, this is just a part of a polyhedron, but there's a natural connection between this sort of smooth differential geometry and kind of discrete differential geometry. And the curvature is a concept that kind of straddles both of them. And I talk a little bit more about this in my algebraic topology series. So I think algebraic topology 16 is a lecture on rational curvature. And Euler characteristic. And you're probably quite fully capable of just having a watch of that video. I recommend it if you're interested in this sort of circle of ideas. So I'm just going to sort of briefly tell you what happens. If you have a polyhedron, let's say with a vertex, so here's maybe I'll draw it in a planar way. So here's a polyhedron, and we're looking at its vertex like that, and has various faces coming in to this central point, but they're not all planar. So this is a vertex of a polyhedra, And let's say there are various angles. So maybe angle alpha 1, alpha 2, alpha 3, up to alpha k. Okay. So in this case here, the angles, so there happens to be 7 equilateral triangles. So 7 times 60 degrees. Okay. And because, of course, there's 7, not 6. If it was 6, they could be made planar. Here there's 7, so you can see that they're not planar. If I took 2 of them away and just had 5, of course, then we would get a kind of a vertex of an icosahedron. Still a bit of flexibility involved, but it can't be planar, of course, because the angles don't add up to 360 or 2 pi, if you want. Okay. So you could imagine something like this, perhaps. Or you could imagine one with 7, or they don't have to all be triangles. Just some general configuration, and there's a vertex there. Now, you might say, well, this is quite different from a surface, but it's really not that much different from a surface, because we could imagine sort of smoothing this. If I dipped it in batter, I could make this smooth. Right now, it's got some non-differentiabilities there, but if I sanded it down a little bit, I could easily make it smooth. And then if we looked at the curvature of this thing, well, we see that in terms of the normal vectors on these planes are going to be completely all in the same direction. And the curvatures are going to be 0 on these faces. In fact, along these lines joining the faces, the curvature will also be 0, because there's this straight line there. This is a parabolic point. The only places where there's non-zero curvature is at the vertex. The natural question is, how much curvature is there at this vertex? Well, if we follow Gauss's kind of thinking, what we would want to do is we want to look at the normal map, or the Gauss-Rodriguez map for such a polyhedron near this point. And so what we could do is we could create normals. So let me draw the normals like this. So these are supposed to be normals to the various surfaces. And we kind of join them. And so you have to imagine, so you have one normal here and another normal there, and maybe imagine the plane that's perpendicular to the edge that goes through that normal and that normal. Okay. So if we look at the image under N, over here is our sphere. These, in this case, 5 normals are going to give us 5 points. And these edges along here are going to give us these edges here. And then the really interesting thing is the total amount of curvature over here, the total curvature, say at the point P, will be equal to the spherical area of this polygon. And we have to know just a little bit. I have to remind you about the spherical area of a polygon. Okay. So I remind you that if you have a spherical triangle on a sphere, and you have angles alpha 1, alpha 2, alpha 3, then those angles don't add up to 180, of course. But the area of the triangle is equal to the spherical excess. It's how much more the angles are from what they should be in the planar case. So alpha 1 plus alpha 2 plus alpha 3 minus pi. And if you had a slightly more complicated thing, if you had, say, 4 points with angles alpha 1, alpha 2, alpha 3, alpha 4, in that case the area of this sort of rectangle, well, it's if you sort of think of it, dividing it up into 2 triangles like this, there'll be a sum of angles minus pi and another sum of angles minus pi. So it'll be alpha 1 plus, well, sum of all the alpha i's minus 2 pi. So in general, if you have an n-gon, area of an n-gon is the sum of all the angles alpha I from I equals 1 to n minus n minus 2 times pi. And let me just rewrite that as 2 pi minus 2 pi minus summation of I equals 1 to n of alpha I minus n pi. So I can write that as pi minus alpha I. So if we go back to this situation here, the area of this n-gon is going to be 2 pi minus the sum of the pi minus the alpha i's, where the alpha, these are the, maybe I should, these alphas are different from those alphas, so maybe Let me call these ones alpha primes. I suppose these are all primes here. So I don't have to change too much, okay? So the area of an n-gon with angles alpha 1 prime, alpha 2 prime, and so on. So here we have alpha 1 prime, okay, alpha 1 prime, alpha 2 prime, and so on. And the natural connection is, what is the relationship between these angles and these angles? Well, if we go back to our polygon, well, actually, maybe you can see it from here. So if we have a look at this, this thing here, and we ask, what if this is angle alpha 1, and this is angle alpha 1 prime right here. This is the angle between these two faces. Then if you have a look at this little quadrilateral there. There's an angle of alpha 1 there, an angle of alpha 1 prime, and these ones here are perpendicular. And this is just a planar situation, which is telling us that alpha 1 plus alpha 1 prime has to equal pi. Alpha 1 plus alpha 1 prime equals pi. So the long and short of it is that this formula over here, the area of this thing here, if I just apply this, it's going to be 2 pi minus the sum of the angles alpha I. And that's the curvature at P. And rather remarkably, this is a formula that goes back to essentially to Descartes. It's actually sort of a precursor to Euler's polyhedral formula, which Descartes almost understood. So Descartes was interested how curved is a polyhedron at a corner, and he understood that this is the relevant formula. So for example, if you have a So for example, if you had a cube, and we're looking at one of these vertices here and ask how much curvature is there at such a vertex? Well, we have 3 sides, each with angle of pi by 2 angles, the alpha i's, and so the curvature at a vertex P will be 2 pi minus 3 pi over 2, for a total of pi over 2. So the curvature at P is pi over 2. And the total curvature of the polyhedron, the total curvature is, well, there's 8 of these. So it's 8 times pi over 2, which is 4 pi. And that's just a discrete manifestation of the same formula that we wrote down over here somewhere. I think I just rubbed off. And you can try it out for the other Platonic solids, or in fact any polyhedron whatsoever. And it's also interesting if you have, let me put this thing back together with 7. So if we have 7 equilateral triangles at a point, then what you get the curvature at P will be 2 pi minus 7 times, well, each one of them is a pi on 3, for a total of minus pi on 3. reflecting the fact that this has negative curvature. This is a discrete analog of a negatively curved surface. There's principal curves going in one direction like this, and other principal curves going in the other direction like this. So in fact, Gauss's formula generalizes not just to convex bodies, but to more general ones. And I might just put the Gauss-Bonnet theorem. The total integral of k ds along a surface is 2 pi times the Euler characteristic. And finally, this really sort of gives some kind of understanding of the theorema egregium. Because when you look at it from this point of view, you can see that the curvature here, which is minus pi on 3, is going to be unchanged if I start distorting it. These distortions here are not affecting the geometry of the surface. If you were a bug, you wouldn't be able to tell any difference in terms of making local measurements. And it looks like I'm changing the surface, but in fact, the curvature at this point is staying exactly the same. That's what Gauss's theorema egregium says, that when you bend a surface, when you distort it, without tearing it or ripping it or something like that, then if you maintain the geometry of the surface, then the curvature doesn't change. So the curvature is actually intrinsic to the geometry and not to the ambient embedding. So this in some sense provides a kind of a simple-minded, discrete-like proof of the theorema egregium, or at least gives pretty strong indication of why it's true. Okay, so there's obviously a lot more things to be done. This is just sort of a beginner's course in differential geometry, but probably this is a good place to stop. So I hope perhaps to teach this course at some future time, and then I will add some more videos well, probably starting off with this stuff here, but there's also lots of other interesting directions to go in. So we'll see you all then.